toothbrushes to automobiles, earbuds to mobile devices, and toys to semi-trucks, lithium-ion battery technology is finding its way into just about everything. As such, the demand for battery materials, innovation in electrode design, improvements in manufacturing, and the optimization of charge density are ever increasing. To stay competitive, manufacturers of lithium-ion batteries are challenged with maximizing battery performance and minimizing cost to keep the adoption of lithium-ion battery technology economically attractive. Inside this episode of the Thermal Review, we will discuss how infrared thermography is being used to optimize lithium-ion battery development, manufacturing, storage, usage, recycling, and even disposal. Good day, Marcus.
Dave, how are you?
I'm good. How are you this day?
Not too bad.
Not too bad. Seems like we just met not too long ago in our previous episode where we were talking about non-destructive testing to today, where we're talking about lithium-ion battery technology and thermography. And we have a special guest with us today. Good day, Jerry Beeney.
Hey, Dave. How you doing? Hello, Marcus.
I'm doing well.
Thanks for having me on this. So looking forward to it.
Well, we're thrilled to have you, Jerry. Thank you for taking the time out of your schedule to meet with us. Again, the topic for today is infrared thermography and how it's impacting essentially the battery life cycle. And Jerry, maybe you can give us a little background introduction. You're a global director of business development for Teledyne FLIR, but what does that mean?
Yeah, so I work within the Teledyne FLIR Solutions division where, I directly kind of focus on markets and applications related to productivity and quality, which, lithium-ion batteries falls directly into. So, I've been with FLIR for, I think, somewhere over 16 years now. I kind of lose count after about 15 there. But I spent about the first 10 years of my career at FLIR selling and supporting, high-end thermal camera systems, kind of across a broad range of different industries and applications. But a number of years ago, I moved into business development where now I kind of use that customer facing sales experience and helping to develop and implement some strategies that really help kind of drive growth for Teledyne FLIR in the future. So I think this is really kind of a great and relevant topic today, especially given kind of that huge global push towards renewable energies and electrification. So I'm really excited to be part of the discussion.
Awesome. Thank you, Jerry. And by way of introduction, we have Marcus Tarrant here with us, as usual, our president and CEO of Movitherm. Marcus, perhaps a reintroduction to our audience?
Yeah, so I'm the founder of Movitherm, founded the company in 1999, October 19th to be exact. So we're in it for 23 years almost. And have been
congratulations.
Thanks. Yeah. I know time is just flying, isn't it? Especially
yeah.
And I've known Jerry for a very long time as well, working with FLIR, Teledyne FLIR now on these science cameras that we're using quite often as part of our solutions, and doing automated thermography and non-destructive testing. And I'm excited to talk about this whole battery topic. Just heard in the news, I think LG is putting a big plan together in the US, I think in cooperation with Honda to manufacture their new battery packs for their new electric vehicles coming up. And then there's another effort. So there's a lot of push in that direction for sure. And we've seen it also in a lot of inquiries lately with battery manufacturing, working on several projects there as well. So I'm excited about this topic today.
Yeah, thank you, Marcus. And by way of reintroduction, my name's Dave Purcell. I've been with Movitherm now about a year, a little more than a year actually, but had known Marcus for several years. And Mr. Beeney as well. In fact, I allude to this often that I used to work for this very large infrared camera manufacturer for almost 20 plus years. And that was actually FLIR Systems. Yeah, so Jerry and I actually go way back when Jerry talked about selling science-grade infrared cameras into the R&D and science space. Jerry and I were actually doing that together as part of the same team at FLIR Systems. And in fact, that's kind of how we met Marcus 16 years ago at FLIR Systems, really needing someone to help out when it comes to developing a complete solution. Whereas at FLIR, we make they make awesome infrared sensors. And Marcus, what his team brings to the table is creating a holistic or complete solution around that technology. In fact, let's start talking about this lithium-ion battery market space. And from your perspective, Jerry, as a supplier, developer of infrared camera technology, now being in the space of business development, I mean, what are you seeing out there, and maybe what kind of role do you see FLIR playing in that?
Yeah, I mean, I think as Marcus kind of alluded to, there's just a ton of funding being put into the complete supply chain for, battery development, battery manufacturing and production to support, electrification and mobility type applications. Especially, I think the ones that most people hear about are, electric vehicle, manufacturing, with a lot of the really large battery manufacturers, looking to develop or build facilities, at different regions globally, especially in the U.S., as a lot of the U.S. government and a lot of the different states, kind of dictate the move towards electric vehicles. So there's a lot of, funding out there, and a lot of money being spent to kind of like spin up on that, all the way from, again, the mining applications all the way down into, the OEM car manufacturers, like retooling, a lot of their car factories to support, manufacturing of electric vehicles. So from a FLIR perspective, I mean, as you mentioned, we basically, design, build and sell infrared cameras. So as we'll see, and I think we'll kind of discuss throughout this podcast, since thermal cameras basically sense emitted thermal energy or changes in temperature, there's a significant number of areas throughout kind of the battery life cycle where thermal imaging can support, from the initial R&D phase basically all the way out to the manufacturing floor, and even kind of like the storage and safety of them as well. So we've seen a lot of interest in that, especially because I think every company is kind of moving in. The automotive industry in general is kind of moving in that direction. Some people are a little bit more ahead of the curve than others, but I also find it very interesting. I say all the time, it's a little bit of a wild west type situation where every manufacturer is kind of doing their own little thing, and that hasn't been really a consolidation of an approach at this point, which from a thermal camera manufacturer is a huge opportunity for us to kind of get in there and use our knowledge to help, end customers be successful in their applications.
Awesome. Thank you, Jerry. In fact, if I'm not mistaken, there's many of the FLIR devices that use lithium-ion battery technology. So it's actually even driving some of the cameras that you guys are producing, right?
Exactly. Yeah. So using the batteries are, very important throughout this. So you can use a camera that's using a lithium-ion battery to look at a lithium-ion battery. So it's a pretty closed loop. So.
Yeah, no, absolutely. Well, thank you for that, Jerry. Marcus, any insight, additional observations from someone who's, utilizing Jerry's technology, if you will, to create these solutions around them?
Yeah, we see beyond electrical vehicle markets. I mean, the traditional cars, if you will, cars and trucks and those kind of things, delivery trucks. Autonomous robots. We see flying cars, or like those human transporting drones, if you will. They go more and more electric as well, and also a big push in the alternative energy storage market, where it's a big issue with solar, because solar only produces when the sun shines, and then the issue is that, well, how do you power everything if you're going off grid? How do you power your coffee maker or something at night, or whatever, your microwave? So energy storage becomes more and more of an issue as well. So there's battery needs all over the place. I mean, energy storage really is kind of the holy grail of this whole alternative energy market as well.
Yeah.
Yeah.
Yeah, that's a good call,
You know,
Marcus, because with a lot of the green energy, they're not necessarily on-demand energy sources. So basically being able to have batteries available to kind of store that energy up so that it is available to the consumer on demand is, critically important. So
Right.
And that principle or that, having power on demand, as I read in our intro, applies to everything from, the toothbrush that I happen to use for brushing my teeth. I want to make sure that that's running when I hit the button, all the way up to keeping my home electrified, especially during the summer months here in New England, especially this week when it's very high humidity. It's almost 100 degrees outside. Having power available at that time as well. Some of our listeners may be aware that there's energy storage or battery storage the size of containers, rail car container size type backup battery storage that's available as backup power to make sure that again, my air conditioning is running, or if a critical operation or process doesn't inadvertently shut down because the power goes off grid or a plant goes off grid. So interesting, very small all the way to very, very large. The principles or physics behind batteries are pretty standard. We're talking specifically about lithium-ion battery technology, but some of this will translate over to other battery technologies as well. I'm going to try to give a real basic background, if you will, to the anatomy of a battery. I don't want to go too deep because this is a podcast, and in our video stream on YouTube, maybe we'll pop in a graphic or something. But very basically, you have current collectors. That's at each end of the battery, right? Your positive and negative. Those are your connection points, if you will. Connection point to pull power from or add power to when you're charging. You have a cathode and you have an anode. And the cathode, it essentially stores, it's a positive electron. It stores lithium ions. And it's usually made from some type of chemical compound, metal oxide. Now, that's probably too deep. The anode, it stores lithium ions as well, and it is the negative electrode, if you will, typically made from carbon. So hopefully we'll have this graphic, and you can see how the lithium ions will travel through the separator. But the electrodes will travel through your device, like a laptop, or if you're adding power, it's coming from the circuit. I hope that makes sense. That's maybe a little too deep. But essentially what we're talking about here is anything that impedes that process of those flow of electrons and lithium ions can impact how well that battery performs. Or if there's something in the manufacturing process that impedes that electron flow or creates like a short, that could lead to something like thermal runaway that causes a whole nother batch of problems with fires. And there was a time when you maybe were seeing commercials or video clips, news articles around battery-powered automobiles igniting and experiencing thermal runaway, those kind of things. So that's a real quick review, just cathode, anode, separator, and electrolytes and current connectors that you connect to the ends of the battery. Jerry, you started to touch on this, and that was the battery life cycle. And it's not just there's a demand for batteries, right? So we need to get batteries. There's a whole life cycle or supply chain, I think is what you called it, associated with that, where you have these multiple phases of the battery life cycle that include, I think you touched on mining and refining. I know, Marcus, you talked about R&D and production, which is another phase. Once these batteries are, let's say, mined, produced, manufactured, then you have to but there's a storage and usage phase, if you will, right? When they're not in use, they're being stored, they're being powered, energized, and then when they're not being stored, they're being used. When these batteries start to increase in age, they start to lose some of their efficiency, but there is an opportunity for recycling. There's a whole market for recycling batteries and reuse. But ultimately and eventually, there is this waste and disposal stage as well. So this is the battery life cycle, if you will, all the way from the mining, the production, the storage and use, to the recycling and waste. And what we're, again, talking about today is how this technology that Teledyne FLIR produces, this infrared thermography technology, can be utilized at the different phases or different stages of that life cycle. And I mean, this could be a very lengthy podcast, quite honestly, because we could drill into even the mining and refining phase, right? We could be talking about what happens there, but we're going to keep it fairly high level. We're only going to talk about a few of the stages like R&D, production, and we'll get into the storage, use, and waste and disposal. By way of review, and we generally talk about this is the thermal review, right? So we're talking about infrared camera systems, but I'm wondering, Jerry, for our listeners who maybe haven't listened to previous podcasts or aren't as familiar with infrared thermography, could you just kind of explain to us what is infrared thermography, and maybe as part of that, how does an infrared camera work?
So for people that don't know or haven't, know anything about thermal infrared, basically everything, is emitting thermal energy. Pretty much anything above absolute zero is emitting thermal energy. Obviously, the hotter it is, the more thermal energy that it's giving off. So basically, a thermal camera utilizes a detector that actually is a passive device that just kind of stares out into the scene and looks to kind of capture that thermal energy. There's different types of cameras out on the market that utilize slightly different detector technologies, but ultimately what it's doing is it's basically taking that thermal energy, capturing that, and then transferring that into an actual signal that we then read off that detector, and then take that readout from the detector and then calibrate that for temperature. So depending on exactly what you're doing, you can do both qualitative as well as quantitative measurements. So it's really depending on the application. Sometimes you maybe just want to see a small thermal change. Sometimes you actually want to measure what the temperature is with a non-contact temperature measurement tool like a thermal imaging camera. So there's a variety of different applications that we can satisfy with it. So it's a fairly basic device. Most of the ones that you'll see out there are microbolometer based cameras. We can think of each individual pixel as being a small constrained beam of it made out of a thermoresistive material. So when that thermal energy comes in and heats it, creates a resistance change. We simply run a constant current across it, measure what its voltage change is, and then we then calibrate that out for temperature, and then represent that as an actual image on the screen, either on the screen on the camera or a screen on your laptop or your computer. So
what's awesome to me is that you described what's happening at an individual pixel or detector element, but in the camera you're doing that to thousands. Is that right?
Correct. Yeah. So basically, the thermal sensitivity of some of these cameras is like a tenth or even 100th of a degree, Celsius change. So we can see very, very small like thermal changes, and then actually calibrate those out for temperature as well.
All right, awesome. You talked about how infrared or the detector is passive. I mean, you're not exciting or sending out any kind of radiation or anything like that, towards the target of interest, right?
No, it's simply just they're referred to as staring focal plane array. So it's a 2D array of these individual pixels that I mentioned, basically just looking out at the scene through a set of optics or a lens or something like that, and it's just collecting that emitted thermal energy off the surface of the material that it's looking at.
Okay, awesome. Thank you. Marcus, last time we were together, our focus was primarily on what we call infrared non-destructive testing. We talked a little bit about active and passive. And Jerry, as you're talking about this, the sensor in the camera being passive, passive thermography is relying upon like the naturally occurring, if you will, heat flow from objects. Correct. And targets. Yeah. But there are sometimes applications where maybe there isn't this naturally occurring. And Marcus, maybe you can describe for us again what active thermography is, where we're leveraging this passive, camera, if you will, but adding something to it to maybe tease things out.
Right. Yeah. To tie this together with, let's say, battery manufacturing or R&D purposes. So a lot of, besides lithium ion, there's a lot of different battery technologies that are being brought to market. They're being explored in the R&D phase, and basically what these manufacturers are trying to do is to try to improve the ability to charge these batteries faster with a higher current density and shortening the time, because who wants to sit at a charging station with their car for 45 minutes, right? So they would like to get on their way in 5. But the problem is you have to get that amount of energy in. That requires a huge amount of current, and then if you have a high resistance inside the battery, that creates a huge amount of heat. So all of these things need to be optimized and managed, so from the energy density. But then on the other side too is when these batteries are being used and discharged. The same thing is true where there's usually a trade-off between either you have a very high capacity battery, but you can only discharge it slowly, or you have a lower capacity battery, but you can discharge it at very high currents. So they're trying to find the right operating point between those by optimizing the materials and electrolytes that they're using. And so that brings us back to the research that's being done on the materials. So that if I'm looking at the materials, what I want to avoid is any sort of imperfections, because like you said earlier, if there are imperfections in the materials, they can lead to thermal runaways, shortcuts, inefficiencies in the process. So I may be misled by making an imperfect battery prototype because there's imperfections in there, and then I may draw the wrong conclusions that this approach isn't working, where I basically screwed up in the manufacturing process. So what we can offer at that stage of the manufacturing or the R&D process is to actually verify that the materials that are being used are very pristine, they're very clean, they're very free of any sort of delaminations or contaminations. The issue with that is that at that point the battery is not in operation, so there isn't really a change in temperature and therefore no what we call a thermal contrast to be exploited in the thermal cameras. You're looking at a piece that is basically probably at the equilibrium portion, meaning it has basically taken on the temperature of its ambient, right? Because it was sitting there for a while, unless somebody touches it with their fingers or something and upsets that equilibrium. But it will probably just sit there. So if you're pointing a thermal camera onto an object that is just at room temperature, you will just basically see almost no temperature difference, and it's just going to be a gray, noisy sort of appearing image. There's no discernible information in there that can lead to any sort of useful data. So that's where active thermography comes in, where we now come in and actually excite that piece of material by any means that are useful. So it could be a tiny little infrared emitter that just creates a little heat spot on it, and we may be scanning across the surface and just observing how what the thermal conductivity changes are on the surface, for instance, over time. And that's where our active thermography comes in, where we actually try to find any sort of changes in thermal conductivity and try to convert that into a result image, which then has that thermal contrast. Although that thermal contrast in an active thermography sort of a system is a little bit different than just saying here's a temperature difference. It's really the relative thermal flow over time. So it's really more it could be more in the frequency and sort of domain rather than in the time domain, depending on what we're doing. But at least that gives us the ability to control what's happening with a material without any sort of self-excitation in terms of temperature.
Wow, thank you, Marcus. Yeah, so you're describing looking at perhaps the electrodes even before they're packaged in a battery to make sure that the electrodes themselves are absent of defect.
Right.
Which, as you pointed out, if there's impurities or contamination or something that's leading to a short, that's going to impair that performance of that battery. So excellent, description too of how that electrode, there's no charge on it, there's nothing going on to it, so it's thermal equilibrium.
Right.
So we provide that excitation. So yeah, in the R&D stage, excellent. Jerry, are there applications that you're seeing out there as well in the R&D stage? Maybe even a little further on down after the electrodes have been packaged. I don't know. What are you seeing, perhaps?
Yeah, I mean, obviously, once the battery cells are actually, manufactured, even in the battery, cell manufacturing process, obviously, you mentioned that, you have, anode and cathode, but you also have like the tabs or the way to basically get basically get the energy to start flowing a lot of times. And this is where it's kind of interesting because there's a variety of different, like, kind of form factors for these individual battery cells, but typically they're doing some type of, if it's like a standard cylindrical cell, they're putting that material in, and they're doing like laser welding around it or something like that. And they actually want to look to make sure or verify the quality of the laser weld when they seal the battery pack up. Or if it's a pouch style, battery cell, that they're basically putting the little battery tabs on. Again, that's a welding process. Sometimes it's hypersonic welding or something like that, or sonic welding, and they just want to look at the integrity of that weld, in the process. So, even from that kind of initial like battery cell production, Marcos is kind of talking about all the constituents that go into it, but kind of throughout that, as they start actually building that up, becomes pretty important to make sure that, everything is done well, because if they have any type of, potential like, gaps or high resistance areas, so those areas of high resistance, once that current starts flowing, can be a problem area where it's starting to heat up. And one of the biggest things is if it's heating up, that is energy that's being lost as heat, and not energy that's actually being transferred to being a useful, electrical energy source for whatever the battery is installed into. And that even scales as you take each individual, battery cell and build them into modules and larger packs. You get more and more interconnections, and whether they're welded connections or mechanical connections and things of that nature. You want to make sure that you have as efficient of a electron transfer in these battery packs as possible, because it directly goes to the efficiency of the battery as well, not just the materials, but it's actually how everything's kind of connected up. And you can imagine if you have thousands of individual individual connections, and each one of them has a slightly higher resistance that is creating a little bit of heat. You start adding up all those kind of like losses in the system, and you're going to drop your efficiency. So small little like efficiency gains on individual components actually ends up having like a huge impact in the overall efficiency of the larger battery like packs or modules too. So
interesting point. No, thank you for that. I mean, we talked initially about this anatomy with these current collectors, but you have to connect to them eventually, right? The anodes and cathodes all have to come together and then connect somehow. These welds, I can't imagine them being very large in size in some instances, Jerry. How can you work with infrared thermography still?
Yeah, so I mean, basically, it kind of depends. There's different applications, and it really kind of depends on the parts and what they're ultimately doing, and if they're where in the process they're looking at it. Sometimes the process, normally, if it's a welded connection that's creating some amount of heat on it, using a passive thermal imaging camera is sufficient, because there's enough thermal contrast there to basically see what you want to see and determine if there's a defect. Other times, because of basically the materials, or they have a high thermal constant or something like that, you need something like active thermography to impart that that thermal variation in order to detect it. So we've seen things where it's anywhere from like I mentioned, like the little tabs on the pouches, all the way up to the full packs where they're connecting a whole bunch of individual kind of D cell batteries together with small little wires. So it's kind of a full gamut there. So
interesting. Yeah. And I know that today with the infrared technology, there's the thermal sensitivity, and there's also, or the thermal resolution, but there's also the spatial resolution as well with these cameras. And I mean, I remember, working in the science department at FLIR, the 4X lenses with high definition cameras resolving down to, was it like 4 microns or something
Yeah,
like
about
that?
4 microns. So that depends. So depending on the infrared camera, obviously the camera has a certain native like pixel resolution, but there's a variety of different like optics or lenses that you can put on the cameras depending on exactly what your target is, what your field of view requirements are, what your individual pixel resolution needs to be to see the specific defect. And sometimes that's kind of fairly simple math to figure out what you need, because if you can think about it, you basically have a 2D array of pixels that are looking through a lens with this kind of a certain field of view. So as you go from the camera and you expand out, that pixel gets larger and larger. So when you start looking for very small defects or something like that, you want to make sure that you have sufficient number of pixels to actually at a size or a spatial resolution to actually see that, or to image that the thermal contrast to see that defect. Because if you have a very small defect and the pixel's really large, basically the camera can't see that sub-pixel thermal change. It's going to basically just read out like the average temperature within that pixel area on your target. But there's a variety of different cameras, from smaller resolution native detectors all the way out to HD resolution cameras with 5x microscope lenses that will get you down to like 3.5 micron per pixel spatial resolutions, and pretty much everywhere in between. And really it's kind of so it really kind of depends on the application, what people are looking at. If they're looking at small individual components, large assemblies, things of that nature. There's a variety of different things that could suit. And I'm sure what you guys Movitherm too kind of depends on that as well. You can tie multiple different cameras together into your system to get kind of that larger mosaic of of the part if you need to.
Yeah, in fact, we've done some work recently with a staging application, taking very small image snapshots, stitching it together, coming out with a huge. I don't even know what the resolution was, Marcus. Megapixel, and then some resolution of these very small targets.
Right.
I'm curious, Marcus. We talked about lock-in. It was mentioned earlier, right? And lock-in is an amazing science in teasing out very, very fine, very small defects. Is there a place for lock-in when it comes to weld inspection on battery, Marcus?
Yeah, there's actually one particular one, like Jerry mentioned earlier. There's different ways of these battery cells being welded together. Some use a very thin sort of a metal strip. Some folks even use that to be kind of like a fuse, where they have a thinner part where, in case there is a shortcut or an overload on the battery, it actually blows up and it just burns up, and it just opens up like a fuse. And then some other folks use little wires. It kind of depends on the design and the concept behind it. But what everybody is interested in is a low resistive weld, right? The connection from the electrode of the battery cell, the anode or cathode, over to the next one, depending if it's a parallel or series circuit. And then it's all usually welded back together to some sort of a bus bar, which is a massive current collector that then connects to something else. So when you have hundreds and hundreds of battery cells there that are in series and in parallel, what's very important is that obviously the current flow is given, and if there is a higher resistive weld, what happens then in that section? You typically have an increase in heat. What is problematic to some degree is these materials. Sometimes it's like nickel wires or something, or nickel coated wires. They are very shiny. So from you guys that know thermography, is like emissivity is a huge challenge, right? So if you have a very shiny metal part that's very tiny, it's very difficult to discern temperature from it, or temperature differences from it, because it's really acting like a mirror. Where active thermography or lock-in thermography can come in there is that it is so sensitive to the tiniest little changes that we can, for instance, doing the load testing, what a lot of manufacturers do, they put the battery packs up, and they're performing a load test. They have charged up the battery pack, and now they're performing an pulse loads on the battery to really drive the battery beyond its specified capacity typically, and trying to do a very violent discharge for very short periods of times. And they do this repetitively, and doing that moment, it's basically make it or break it sort of a test to just full on stress the pack. Doing that test, we could log into that discharge moment and then see any sort of temperature changes. And the advantage of using lock-in thermography there is that it actually the algorithm of lock-in has like fast Fourier transform algorithms built in, and it tends to only respond to the frequency of excitation. So it really just filters out any sort of reflections and everything else, and what you're left with is really just the temperature changes, expressed in a phase angle. If you look at the phase image, and you can really easily see where's there a weak weld, without having any sort of reflection issues and that sort of thing. So that's where that becomes very useful at the end of line testing of battery packs and those kind of things as well.
Okay, awesome. Thank you. So we've talked a lot so far about the R&D manufacturing stage, if you will, of that life cycle. As I mentioned, we could really drill in and spend a lot of time just focusing even just on the R&D production one. I'd like to shift a little bit and talk a little bit about storage and use. So that's after the battery's been manufactured and they're in a setting somewhere where charging and discharging, maybe even just sitting, waiting until that power draw is needed. Jerry, what are some of the things that you're seeing, and how can infrared impact this phase of the battery life cycle?
Yeah, I mean, I think obviously, I mean, like Marcus mentioned a little bit about thermal runaway. So for people that don't know, thermal runaway is basically a situation where kind of the battery or cell, has something happen to it where it kind of reaches a critical temperature, and that temperature actually triggers a chemical reaction inside the battery that generates like even more heat, and then that increase in temperature further accelerates that reaction, creates kind of a little bit of a feedback loop of ever increasing temperatures, to the point where like a fire or like sometimes even an explosion, if there's a lot of pressure that builds up in the battery, can actually happen. So it's something that people are aware of. So if you've ship something around these days, like a piece of electronics, they'll ask like what battery is in it, or heck, if you've flown on a commercial airline flight recently and they talk about if you lose your phone in the seat, don't move anything, because they worry about basically, damage that can actually impart or create one of those thermal runaway conditions. So when these batteries are basically like assembled, and stored, there's a huge concern with, something within that battery, whether it be an internal defect, like what Marcos is talking about in the constituent materials inside that battery, or some type of like damage that happened that triggers a little bit of a thermal runaway condition in the battery, or a temperature rise in that battery that raises the temperature just enough that now it also proliferates across like all the different batteries, that it's being stored with. And you can imagine it's basically like, throwing a match like into a whole bunch of, tinder, or out in California with it being so dry or something like that. It just could spread like wildfire. And I think one of the largest concerns with it as well is that battery fires, and specifically lithium ion battery fires, are very difficult to put out as well. And there's also a concern with basically the outgassing and chemicals and stuff that are in there. So it's very dangerous, not only for the plant and the workers, but also the firefighters that come. So we've seen a really large uptick in kind of like storage and monitoring and looking at those storage facilities to make sure that everything is, kind of in a good steady state, and that there's not anything in particular happening with it. And I think you guys actually offer kind of an intelligent early fire detection system that kind of does that. Is that correct?
It is. In fact, Marcus, I don't know. This is. I think this is a great example. I mean, the others were examples too in the R&D phase, right, where FLIR is producing a camera it works very well in passive thermography type applications, but maybe if you need just that much more, Movitherm has this capability where they can apply some active excitation and then some additional science through a lock-in software and evaluation to really, take it to the next level, if you will. And this is another great example of where FLIR is putting together, building an awesome sensor, a camera, and these cameras are so great because, again, it's non-contact temperature. And as Jerry, you pointed out, it's both qualitative and quantitative. So just visibly, you can look at a thermal image and say, there's something there getting hot. And then because of your technology and calibrating it to measure temperature, now I can put a crosshair on it, or I can draw a little area and say, give me the maximum temperature there. Now I'm quantitatively pulling out that information saying, oh yeah, this is hot. I should investigate this. And this is where, what we're doing at Movitherm, which we call IEFD, which is intelligent-based early fire detection, is essentially taking your sensors and wrapping some stuff around it. Maybe, Marcus, you can talk about the stuff that we wrap around it, which creates that complete solution for the customer. I think we could talk about the different applications.
Right. I think the application, from tying it back to the battery topic, there's really three different stages for these early fire detection applications. So one is really the storage, just to make sure that if you're storing large amount of batteries and stacking them on top of each other, you want to make sure you don't hit that thermal runaway, because maybe your forklift ran into a pack on something and did some physical damage, and it's slowly running away and you don't notice that. So the storage for still batteries that are being shipped or being used. Then we have the charging stations. We have a lot of customers that have charging stations where they have either electrical forklifts or they have scooters or whatever the case may be. We've had a customer that has a whole charging rack for mobile devices. They have a large team, and we had like a 64 bay charging station where they just put their mobile devices in and they wanted to do fire monitoring there, that sort of thing. And then doing the recycling as well, which is also typically a storage situation, but typically recycled or batteries that are being discarded for recycling already have more damage to it as well. So those are kind of starting from the application point of view, areas that we serve there. And then going back to what Dave said in terms of the intelligence that our system has, we have a cloud-based monitoring system where we can tie in as many thermal cameras as we need to look at those critical areas. And we have kind of a hybrid situation where we have an intelligent gateway that sits on the factory floor that has logic running that talks to these cameras kind of in real time, and then uploads to our cloud, sporadically, like every few minutes or so, to keep the data load down. And then if something happens, then the data rate increases. That's kind of where the intelligence comes in, and we can actuate fire suppressants, like especially for a storage facility that does lithium ions. They have special fire suppressants that are obviously not water based, because that's not a big no-no for those cells. So we can do that sort of thing, and you're getting notifications via text message, voice calls, emails, those kind of things. And so that helps out these companies to find their peace of mind, to make sure that nothing happens, let's say during the weekend, if the facility is not in operations but the batteries are there, to make sure that nothing is happening there.
Thank you, Marcus.
I think you make a good point too about the. Oh, sorry, Dave. Yeah, I was just going to say, I think you make a good point there with respect to, the charging and discharging or the fast charging too, because as you mentioned, I mean, there's a little bit of an interplay between, wanting to charge recharge the battery as quickly as possible, but that's also at a risk, so yeah, we've had a lot of people that do, either real-time monitoring of those charging stations, or just kind of from an R&D standpoint to figure out, all right, how fast can we recharge these batteries and not hit that thermal runaway threshold and a little bit below, because obviously people don't want to, wait for, 45 minutes or a couple hours to, to recharge their system to use it again. So they're trying to, dump as much load into it as possible, but yet not actually hit that threshold and still be safe about it. So it's a huge, area that people are using like thermal cameras for, all the way from that kind of R&D phase to figure out what they can do to actually monitoring it when it gets fielded out on the factory floor.
Yeah.
And it's so connected and tied together, right? I mean, if there is an impurity or defect or something happening at the electrode level, and then you get later down the line in the storage or usage phase, and like you said, you're really stressing this battery, charging it. Again, anything that's going to affect that flow of electrons and ions that can potentially increase temperature and then introduce that thermal runaway, develop a short, increasing the temperature, running to that thermal runaway. So all of it tied together. Marcus, you touched a little bit on recycling, and we've talked about this before, how there's battery recycling, and then there's other types of disposal and recycling. And part of the challenge that other recycling centers are facing, or disposal centers, is that they're finding some of this battery waste ending up in their waste streams. For example, metal recycling.
Right.
And maybe you could talk a little bit about that, Marcus.
Yeah, we have a customer that actually had pretty severe fires in a metal recycling facility where there were batteries discarded. Where you're supposed to take the batteries out before you recycle stuff, but not everybody does. And at first, when I heard about this application, I was like, metal recycling, what do they care if they have a fire? Because it's just metal. Metal doesn't burn. But it turns out they have a lot more than just, it's not as clean as you might think. There's a lot of rubber components in there and other materials and solvents and everything else. So yeah, the whole pile can easily light up, if given the right ignition source. And those lithium packs are, the perfect storm waiting to happen. And the problem is they sit in there and they're getting hot. And it actually takes quite a while before something is happening. And then they're reshuffling the material around and dumping more stuff on it. And every time that battery pack gets impacted again, it's just getting that much closer to igniting. So with our early fire detection, we can actually detect hotspots, and they can just go there and actually locate this halfway damaged battery pack from a cell phone or whatever the case may be, maybe a battery drill or something, and actually remove it from the pile and prevent like catastrophic fires. Because this one facility had a multi-million-dollar sort of a fire going on. I mean, they shut half of the city down because there was so much smoke development. The EPA came in, the Environmental Protection Agency, and fined them all kinds of things, because it's not just the fire and all the smoke development and all the toxic gases that blows through the neighborhood now. It's also, now that you're actually dousing the whole pile, now you got toxic water runoff, and that creates a secondary environmental issue. So it's a huge issue. And then you have the insurances coming in, and I mean it's just something that absolutely needs to be prevented, and that's kind of where where we come in with those solutions.
Well, thank you, Marcus. As I mentioned earlier, there's many stages or phases, if you will, of this battery life cycle, and today we've really just talked about a couple. I guess the question I want to ask before we wrap things up is I guess where do you see us heading? Where do you see thermography? Where do you see this battery technology? What I guess I'm curious as to what some of the trends or things are that you see happening and where we're headed. And maybe we'll start with you, Jerry, working out there in business development. What do you see some of the trends to be and where we're headed?
Yeah, I mean, I think right now, I think as I mentioned before, it's a little bit of a wild west, because everybody's trying to play catch up. and exactly how they're doing it, and everybody's kind of approaching it different ways. I think as we kind of move forward, there's going to be a lot more like learning that goes on from the actual, throughout that whole like product lifecycle value stream aspect on where they can be successful with it, not only in, using technology like thermal imaging to, make quality products, but also kind of, have like safety, built into it as well, to the point where, maybe there's a little bit of a consolidation within the industry with respect to approaches with it. What I've seen is basically different global regions kind of have different ways of approaching it and things that they kind of care about, where some manufacturers, some regions are more, care more about it from a quality control standpoint, production throughput standpoint. Other regions care a lot more about kind of the safety aspect of it, not just from a facility safety, but a worker safety aspect of it as well. So I think as right now we're kind of in that almost like startup phase where there's so much, funding being dumped into it. So many companies are kind of playing from behind a little bit. All these new facilities and factories, like Marcus mentioned, are being built. People are just trying to very quickly solve some problems the best way that they can with, using thermal imaging, lock in whatever they can. But I think as the industry matures a little bit, there'll be a little bit more consolidation, a little bit more, testing standards and things along those, to really make sure that everyone's kind of approaching it exactly the same way. And from our standpoint, we're just seeing really kind of that the beginning of it from a thermal imaging standpoint, where it's being driven a lot of times from both directions. It's basically from the users of the batteries to the manufacturers of the batteries, as they just try to figure out the best way to satisfy this huge need that's being created globally as we move towards, the need for like, efficient energy storage type thing. So we've seen a really large uptick in our business, that's not even tracking with funding that's out there, just as basically they're trying to, all the manufacturers and everything are just trying to find the correct tools for the job. And we're just, like yourselves, just trying to help them be as efficient at, solving their problems as possible.
Excellent. Wow. Thank you. Marcus, same question for you.
Yeah, I see. I second that. That's definitely, there seems to be definitely a scramble for solutions. There's also a lot of education that we still need to do, which hopefully this podcast is filling a little bit of that gap to help people understand what they can do with infrared thermography here. And I see a lot of what surprises me to some degree. I see a lot of startup companies trying to tackle these problems internally. So they have a bunch of young engineers there. They're maybe fresh from college. They're trying to just like, okay, how hard can it be? And then they're just trying to, we introduce them to thermography, and they're like, oh, we're just going to develop our own solution in house. And I'm like, why? Because we can, right? So that's, but then I'm like, okay, is that really a smart move? Because these engineers, they're very smart. Don't get me wrong. I don't want to minimize their position in their company. However, there's a difference between being smart and having experience in something, right? So, and then the second question then becomes, okay, they basically have to go through all the learning curves and everything else that we went through a couple of decades ago, and making the same mistakes and learning the same things and everything else. And from a return on investment calculation, I know that wages these days are being sometimes overlooked as, well, nobody looks at the real cost because we have to pay this engineer his salary anyway, so therefore it doesn't cost anything, sort of a short-sighted kind of a view, which I can hear resonating sometimes, which is obviously not true, but that's kind of what it sounds like, versus hiring a consultant. Oh, now I got to dish out some money for this consultant. But then the issue then becomes that we often get then called back when they get stuck. And then they're like, oh, well, this is not working, and your camera's not working, and that's not working. Where it's really not a not working situation. It's more a you don't understand what you're doing kind of a situation. And therefore you draw the wrong conclusion. And then you may actually discard that as a possible solution because you drew the wrong conclusions on this thing. And that's very hard for us to navigate as a supplier. Like, how do we help these folks out? On one hand, I mean, as much as I like to educate, but I can't take hours and hours and hours out of my week to teach somebody how to develop a system that we offer as an off-the-shelf solution, if you will. That doesn't make sense. Um, so I see that sort of a trend happening, and I'm wondering sometimes, is management in these companies, are they aware of what they're doing, and also how much is that distracting them from their core competencies and their core focus? Like, well, if they are a battery manufacturer or an electrical vehicle manufacturer, why do they concern themselves now with trying to do inspection technology that's really just incidental to fulfilling their goal? Like, why do they tie valuable engineering resources up to trying to solve a problem that other companies have made it their life's mission, if you will, to provide? That somebody needs to explain that to me, because I haven't really quite understood where their thinking is coming from.
You've seen that in more experienced companies that kind of know what they don't know. Obviously, as you have a huge number of people that are retiring in the baby boomer generation, they kind of need a lot of that intellectual knowledge has kind of moved outside of the company. So they need people like you that can provide solutions, taking like a Teledyne FLIR piece of hardware, implementing it into a solution that can be deployed to kind of untrained workers that can kind of provide that like results out of push of a button that they don't have to have any real kind of training for, and that the
Right.
results are just immediately available. But going back to your comment about the startup type stuff, I find that even in like larger companies that you would think that they would have a singular vision and a singular path towards an approach, that depending on which group you talk with, they have, a completely different approach, for the application versus like a different group at a different part of the business are going completely in a separate path with it. And there is no singular, voice. And at what point does that divergence actually come back to an actual workable solution for them? And trying to wrangle that sometimes can be a little bit of a political challenge internally with some of those companies as well.
Yeah, absolutely. Yeah,
excellent points.
you mentioned the more mature companies, they know what they don't know, but there's these 4 stages of knowledge, right? Well, like when you're very young, you don't know, right? Then if you're going towards your, like, let's say teenage years and a little bit further, you know everything. And then it gets into you. But the third phase is almost more dangerous, and it's like you don't know what you don't know.
Yeah.
And then it gets into you know what you don't know. You know what I mean?
Yeah.
And that's what we see, that you don't know what you don't know, and then that's the most dangerous phase, I always think, as an outside observer. We have the tools, we have the knowledge, and then we're like, no, we got it, we're just going to develop this in-house. But we still sell the camera, we're trying to support the effort, but then we see the efforts are just like, it's I don't know, we would like to help more, but we're not allowed to help more because they want to handle it all in-house. And it's like, it's hard to watch sometimes, to just
Yeah, it is hard to watch sometimes. I'm trying really hard not to put on my strategy hat and talk a little bit about the importance and need of focus, right? And sometimes that's what it boils down to, right? And you mentioned this, Marcus, is like our company has a mission and this is what we do. It's sometimes the hardest thing to do as a company, and maybe even as an employee of a company, is saying no to things in the spirit of staying aligned or focused on whatever that mission or strategy is.
Right.
It's the hardest thing to do. By not doing it, though, you can make a sacrifice in both your efficiency, which is what you're touching on, and I also believe in your effectiveness of what your desired result is, right? So
Right.
I'm getting a little strategic now, but that's where I love this partnership, if you will, that Movitherm has with Teledyne FLIR. And it's been in existence now for 16 plus years. And both Jerry and I, and Mark, well, we were all there. We all played a role in initiating that relationship years ago, because there was a need for a customer, a problem that needed to be solved, that as a provider of this thermal imaging sensor technology, we couldn't complete it, if you will. So that's where that partnership started with Marcus, who could wrap this solution around this infrared technology that FLIR does very, very well, to create something that is more out of box, if you will, for the customer, so they can stay focused on their strategy, on their mission, and not get derailed in the minutia of things. And, Jerry, I know this is the same at FLIR. We sign NDAs with just about everybody. I think it's 99% of the customers we work with, and we respect that, and we protect that intellectual property in that we share in, and we never share that. But as we're working and solving problems, we gain experience and knowledge. It doesn't give away trade secrets. It doesn't give away, somebody's IP, but it does allow us to make better solutions, make them more effectively, and make them more efficiently. So I think that's an interesting point that you bring up, Marcus. And I've been in discussions before where we talk about the speed of innovation and how it's accelerating. Things are changing so rapidly. What was it? Justin Trudeau said, the rate of change will never be as slow as it is today. It's only going to get faster. And so having this opportunity, this ability to plug in with folks who can provide solutions and bring in that expertise. And I agree, Jerry, I think that aging, very knowledgeable workforce is moving on, and it's being replaced with a different workforce, just different, but maybe more reliant upon that expertise of FLIR and of Movitherm and others. Sorry, got a little philosophical there.
No, and you make a good point though, Dave, and it is one of those things where we obviously have both Teledyne FLIR and Movitherm have the ability to kind of take what is happening out in the industry and in the different applications without exposing IP, but kind of aggregate all those requirements into a solution that we can kind of better everybody with. And that's probably one of the biggest challenges I think everybody sees sometimes is and I think Marcus touched on this, is getting people to appreciate the experience that's behind the solutions that we provide isn't basically because of one person. It's an aggregate of what the market and the applications our customers kind of need, as a whole, to kind of building that a little bit, a trust for a little bit of that, to get people to, and end users to kind of appreciate that there's behind this one product or this one solution, there is so much experience and knowledge that factors into that them to try to climb that mountain is a pretty significant advantage. That just plugging in and giving a call to yourselves or Teledyne FLIR to kind of just talk about the application and potential hardware solutions with it will definitely accelerate their innovations. So
no,
absolutely.
Thank you, Jerry. Well, I think this has been a great discussion, but I think that wraps up this episode. I had this thought, and I guess I wanted to share this as we close here. We do have a lot of experience here, not only in this podcast, but within our organizations and companies, and we don't expect you to just rely upon us in blind faith, if you will. We are all about educating and helping our customers, and many times we think of them as partners, enhancing their awareness and their knowledge. And in that spirit, if you're interested and want to learn more about infrared thermography, there's no better place than to touch base with the folks at Teledyne FLIR. Their website has a huge knowledge base there that you can plug into. I've seen some of the articles and information, Jerry, that's there on your guys' website about fire detection, battery, automotive. I mean, it's vast. But you've got a guy like Jerry Beeney that you can plug into, and I don't know how many field salespeople you guys have now, but it's got to be huge in the U.S.
I've lost.
alone.
Lose count, but there's a lot of feet on the street. Yes,
but there's this resource
both directly with Teledyne FLIR, but with like partners like yourselves as well. So
yeah, so I guess I'm saying don't just take it in blind faith. Plug in and talk to us. And if you can't find the resources that you're looking for to get spun up on infrared thermography, whether it's cameras, the different kind of cameras, the different detector technologies, the wave bands, those kind of things, applications, please, reach out. You can find that information. And the same thing goes if you're interested and want to learn more about this active thermography, you can go to the Teledyne FLIR guys as well. You can come to Movitherm. I love our website. One of the things that I noticed right away when I came on board with Marcus was just the knowledge base library is huge, and it's amazing. There is information there very specific to non-destructive testing, active thermography, and there's information there very specific to battery life cycle, and early fire detection. So I'm extending that invitation to our listeners and all to please plug in, leverage this knowledge that's here, and don't hesitate to call. We are more than happy to talk with folks and help you solve problems. That's what we're here for. Jerry, Marcus, thank you again, and thank you for our listeners for joining us to listen how thermography touches the different stages of the lithium-ion battery life cycle. We invite you to subscribe, to this podcast on your favorite platform, whatever that is. We also broadcast the video edition of this podcast, and Yadira, who produces things behind the scenes here, will see if she can even put in some graphics and things in the video portion, or I guess a version of this podcast to even enhance more education and knowledge. But Jerry, any parting remarks to our listeners before we let you go? And thank you again for taking the time to join us.
Well, yeah, thank you for the invitation, and thank you, Marcus, as well. I think this has been really good. So, yeah, as Dave mentioned, if you have any interest in just kind of discussing your application from a thermal imaging standpoint, feel free to reach out to myself or anyone at Teledyne FLIR, or if you even wanted to have conversations, about solutions with whether it's even passive or active thermography, or even just, thermal cameras in general. The folks at Movitherm are a great resource as well too. So, but yeah, thank you. And thank you for listening to us today.
Yeah. Thanks, Jerry.
Thank you, Jerry.
Good to see you again.
Marcus, any parting?
Definitely fun. Again, I'm excited to see our podcast evolving. I think this is going to be episode 5, I believe. And
episode 5.
Thanks, Jerry, for being a guest here on this podcast. Really, our first external official guest.
We'll see if you invite me back. So
yeah, we're trying to obviously improve our podcast, and hopefully folks find it valuable what we have to say, and discussing these things. We're open to any sort of suggestions from our listeners as well, if they want to hear about any particular topics that are related to infrared thermography, quality testing, any sort of things that they have in mind. We're always open to looking at that, and maybe making this part of our next podcast as well. So I encourage everybody to leave comments, maybe in the YouTube section if you want, or in any of the podcast sort of distribution channels, whether that's iTunes or Audible or whatever else is out there, Spotify, I think. And also go to our website at www.movitherm.com for any more information. And yeah, I'm excited can't wait for the next podcast, and we'll see what's up next for us.
Excellent. Thank you, everyone.